in Chapter 3, Part 4, we're going to think about the empirical analysis. So we want to start to think about how can we determine the molecular formula from data we could collect in the lab. So the first thing we're going to think about is percent composition. So percent composition can be calculated percent composition is equal to the number of atoms of an element multiplied by the atomic weight of that element divided by the molecular weight. Then we're going to multiply by 100. So all this is saying is that the percent composition is similar to the percent by mass. So we are calculating what percent of the mass comes from any given element. So in this example, we want to calculate the percent by mass for carbon, hydrogen, and oxygen. So it's kind of simple. First we need to calculate the molecular weight, which is carbon, 12 carbons, 22 hydrogens, and 11 oxygens. So it's 12 times 12.01, 22 times 1.01, 11 times 16.00. So the molecular weight in this case is going to be 342.34 grams per mole. So the percent by mass for carbon is going to be 12 times 12.01 divided by 342.34 multiplied by 100, and that's going to give us 42.10%. So all we're looking for is the mass that is accounted for by carbon divided by the total mass. So now we're going to do this for both hydrogen, and then we're going to do it for oxygen. So the hydrogen is 22 times 1.01, still divided by the same total mass of 342.34, multiplied by 100, and that's going to give us 6.50%. So from here, this is good. To calculate oxygen, you could take 100% minus 42.1 minus 6.5. Or we could do the calculation again. 12 times 16.00 divided by 342.34 multiplied by 100, and that gives you 51.40%. So we can calculate the percent by mass for any compound provided we have the molecular formula. So the next thing we're going to think about is how we could use the percent composition to determine the next. So if we know the percent composition, we can in fact determine the empirical formula for a compound. Now, if we also know the molecular weight, we can calculate the molecular formula. So this requires us to remember that the difference between an empirical formula, go over here, an empirical formula is the lowest whole number ratio of a molecular formula. So if we have a molecular formula, in this case, let's create something that looks like this. We have C6H4O2. So in this case, this would be our molecular formula. Our empirical formula is going to be, all of these can be divided by 2, so it would be C3H2O. And so it can't get any smaller. Now, we can think about this, that we could create a ratio. So the molecular formula divided by the empirical is equal to a whole number. So in this case, if we were to have the mass for both of these compounds, when we divided them by each other, we would have found that it was equal to 2. And so we can convert between the two. We're going to do a couple examples. So these are related by usually small, but not always, whole numbers. So we aren't going to do that in this first example, but we're going to calculate the empirical formula. So if we have a compound that is 74% mercury and 26% chlorine by mass, what is the empirical formula? So empirical formula requires a couple of different steps. So I think that there's a plan of attack. So the plan, first step, is we're going to assume that we have 100 grams. So the reason we're going to assume that we have 100 grams is because it's going to make the math easier. I've also seen people do this with 10. It works really well with 100 because we can just convert the percents to grams. 2, we are going to convert to moles. And then 3, we are going to determine the mole ratio. So in this case, it is relatively simple. I'm going to move this up a little bit and try to make it smaller so we can still see it. So our first step, we're going to assume we have 100 grams. If we have a 100 gram sample and it is 74% mercury, that means we have 74.0 grams of mercury. Okay, and 26 grams of chlorine. So step 1, done. Now we want to convert to moles. Okay, well, we know how to do that. So we're going to use the molecular weight off of the periodic table, which is 200.59 grams in 1 mole of mercury. And so that gives us 0.369 moles of Hg. Okay, so next we're going to do the same thing for our chlorine. And it is 35.45 grams in 1 mole of chlorine. And then we're going to get 0.733 moles of chlorine. So now we've completed step 1 and step 2. The third step is to determine the mole ratio. Or you could say divide by least moles. So we know that an empirical formula or any formula has to have whole numbers. So what we're going to do is we're going to divide both of these by the quantity with the least number of moles. So that would be the moles of mercury. So 0.369 moles, 0.369 moles. So this equals 1, and this equals 1.98, which is approximately equal to 2.0. So our empirical formula is HgCl2. So what we've done here is we've taken the percent by mass and we converted it to 100 grams, and then we converted to moles. From here, we looked at to determine the mole ratio. Now, it can get kind of tricky because we can also start to think about what does this mean and how do we calculate that. So in this next example, we're going to again calculate the percent composition. So we want to think about the composition for platinum and potassium. So we are given a formula here. So we need to first calculate the molecular weight. And so there's 2 potassiums, 1 platinum, and 6 chlorides. From the periodic table, we know that that's 2 times 39.10, 1 times 195.08, and 6 times 35.45. That gives us a molecular weight of 485.98 grams per mole. From here, we can again, calculate the percent composition for both potassium and then for platinum. So I am going to move this up. So for potassium, it is 2 times 39.10 divided by 485.98 times 100, and that equals 16.09%. So the next one asked about platinum. So platinum would be 195.08 divided by 485.98 times 100, and that equals 40.14%. So to calculate the mass percent or the percent composition, we need to determine the total molecular weight, which is just adding up all of the components, and then we divide the mass that accounts for that element by the total mass. So in this example, we're going to look at ascorbic acid. So ascorbic acid is 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen. We want to calculate the molecular formula. Then, using a different analysis technique, the molar mass was determined to be 176 grams per mole. What is the molecular formula? So in this case, it is going to be relatively simple. We're going to calculate, we're going to do our first step, which is the 100 grams. So for carbon, we're going to take our 40.92 grams of carbon, multiplied by divided by 12.01 grams and 1 mole of carbon. And that gives you 3.41 moles carbon. Next up is hydrogen. So there's 4.58 grams of hydrogen divided by the mass, which is 1.01 grams in 1 mole. And that gives you 4.53 moles of hydrogen. Next, we're going to look at oxygen. And there are 54.50 grams of oxygen. And there's 16.00 grams in 1 mole. And that gives us 3.41 moles of oxygen. So we've completed steps 1 and 2 of our plan. So the third step is to divide by the least moles. This should have a decimal point in there. So we know that the least number of moles for both of those is 3.41. So we're going to divide by that. So when we divide by 3.41, we get 1. 3.41. This equals 1.32. 3.41, and that also equals 1. So we need to think about what's happening with this 1.32. So 1.32 is also equal to 4/3. So we need to do fraction math. Now, fraction math is going to allow us to convert 4/3 into a whole number. So we're going to multiply through by 3. So everybody will get multiplied by 3. So our empirical formula is carbon 3H4O3. Now, a note about these fractions. They will be easily identifiable fractions. thirds, halves, and quarters. Occasionally we'll see fifths. So if you were to get 0.4, that could be 2/5. Most of the time we'll see thirds and halves and quarters. You multiply through. So what that means is we would have taken our 1, our 4/3, and our 1 and multiplied all of these by 3. So that allows these 3's to cancel, which gives us 3, 4, 3. And that is what we get in our empirical formula. So the next part of this question says the molar mass is 176 grams per mole. What is the molecular formula? So it turns out, if you remember, that the molecular divided by the empirical is going to equal a small whole number. So if we have the molecular weight, which if we look back at the problem is 176, and we need to divide by the empirical weight, well, we can calculate that. So that's going to be 3 times 12.01, 4 times 1.01, and 3 times 16.00. And so what we're going to get here is 88.07 grams per mole. So we can take that back over here and take 88.07 grams per mole. And this is going to equal 1.99, which is really, really close to 2. So we know that the empirical formula is basically half of the molecular formula. So the molecular formula is going to be C6H8O6 because the molecular weight divided by the empirical weight gave us a small whole number. So we can multiply the subscripts by that in this case. So let's do another example. In this example, analysis of a sample of mescaline determined that it was 89.92% carbon and 10.08% hydrogen. So the first step is the 100 gram assumption. So we're going to take 89.92 grams of carbon, divide by 12.01 grams in 1 mole, and that equals 7.48 moles. For this one, we're going to have hydrogen. So we're going to have our 10.08 grams of hydrogen divided by 1.01 gram in 1 mole, and that equals 9.98 moles. So we're going to divide by the least moles, which will be divided by 7.48, divided by 7.48, which this gives us 1, and this gives us 1.33, which is very similar to what we saw before. And so now we're going to take our 4/3 and multiply through by 3. And 1 by 3. So in that case, we're going to get our empirical formula, which is C3H4. And so now we have the empirical formula. So, but the question doesn't actually ask for that. It asks for the molecular formula of this compound. So now we need to take our molecular weight, which is 121, and divide our, so if we remember, it should be molecular divided by empirical to give us a whole number. So we have an empirical compound. The empirical weight is 3 times 12.01 plus 4 times 1.01 which gives us 40.07. So 40.07 is going to give us 3.02, which is close enough to 3. And so our empirical formula of C3H4 is going to become C9H12 when we multiply by that factor. So we can use both of these together to calculate this component.